In the propositional calculus, we work with variables, expressions called propositions. They're the fundamental units that we deal with. And these only have two values. They can be true or they can be false. This is different than real valued calculus, where our variables can take on an uncountably infinite number of values, any of the real numbers. Here, we're working with variables that can only be two values, t and f. We combine these variables with what we call connectives. We can think of them as logical operators. There's not, which will change the value from true to false or from false to true. This is a unary operation. This is just applies to a single proposition. Then we have and or. We call and conjunction, and we call or disjunction. These are logical terms from that community. We will use these again in our mathematical CS presentation, but usually we can just use and or. You'll notice that these symbols are inverses of each other, and when you're first learning this, first getting used to what all of these symbols mean, it can take a little bit of time to get straight in your head that the upside down V is and the normal looking V is or. It may help to relate these back to the union and intersection symbols from set theory that you're used to, because we know that the intersection of two sets contains all elements that are in one set and in the other, while the union of two sets consists of all elements that are in one or the other. Implies is the arrow. This one's pretty straight away to understand. We're going to be using these four connectives in our propositional calculus. Instead of using a plus sign or a multiplication sign or a minus sign, we're going to be using these symbols to connect our individual variables or propositions. We call the proper ordering of propositions and connectives a well-formed formula. Now, for the most part, this is just going to be something that you see and don't have to worry about too much, but the textbook has it all throughout. We talk about these. We say something is a WFF all the time. So all that means is that you have combined your variables with your connectives in a way that is valid. So for example, I can write P implies not Q, or not P and Q imply R. P implies not Q or R. Now, we may need to think a little bit about these. What is the proper order of operations here? So when I have not P and Q, where do the parentheses go? Is that not P and Q? Or is this not P and Q? It turns out that these are listed here in the order of precedence. So we first apply the unary not operation. So that means that the not attaches to the P. It does not attach to the P and Q because not happens first. So P is knotted, and then we and it with the Q. The and comes next, and or. You can think of and as multiplication and or as addition. It's the same ordering as in scalar calculus. And then implication is last. This is really important because this keeps us from having to put everything on the left or on the right side of an implication in parentheses every single time. So when we see not P and Q, that means this. It means not P and Q is in parentheses, and that all implies R. And for this other one down here, P is implying the entire right-hand side of the implication side. So just read this a little bit, and it'll come to you. It's not the most complicated thing, but this is new. I mean, it's a bunch of new terminology, a bunch of new symbols. It takes a little bit of time with it. This is why reading through the book, just exposing yourself to these sorts of equations, this new kind of calculus is valuable. We do have a mathematical definition for what a WFF is, and if you're into math, if you're a math major, if you have a math background, then this sort of thing makes a lot of sense to you, and this is very pleasing to you. You feel comfortable with this sort of framing of the definition. But basically, as long as you understand that if you have V and W, which are well-formed formulas, and you combine them in a sensible way, the way you would expect, then you get a well-formed formula out of it. Here's some more examples just to indicate more clearly the order of precedence up here. If you have not A and B, then the not A is in parentheses. If we have an or and then an and, the and happens first. Just like if this were a plus sign and this was B times C. If this was A plus B times C, we evaluate the B times C first. And then the implication, we evaluate everything over here on the left side before the implication. And if we have multiple implications, then things evaluate from left to right. So A implies B comes first, and then implies C. You can throw some nonsense together that's not a WFF, right? Like here you've got a not, and then you've got the implies. That doesn't make any sense. We can't negate the implication symbol. That's nonsense. Over here we've got R times RP just together. We don't do that in the propositional calculus. We've got a or that's just hanging here with nothing else over there. We don't do that either. So it's not that difficult to really obviously see things that are not well-formed formulas. We have a great advantage in the propositional calculus because all of our variables take one of two values. This means if we're looking at a function here, let's say P and Q, we'll think of this as a logic function. Whereas in the real valued calculus, if we wanted to plot something like y equals x squared, we can only approximate the plot. We have to use arrows to indicate that this goes on forever in both directions because the x-axis is infinite in length. In propositional calculus, that's not true. In the propositional calculus, I have two independent variables here, P and Q, but rather than having an infinity of possible inputs, I only have 4. These are all possible combinations of the two values that P and Q can take on. So this means I can draw up a table that has the truth value for this function. So P and Q is true only when both P and Q are true. And so this will completely describe the logic function. P or Q, this is pretty straightforward as well. It's worth noticing that on this first one, we are using our logic or in a slightly different way than is typical in normal English. If someone asks you, do you want cake or do you want ice cream for dessert? And you answer with yes, you are not considered a logical mastermind, you're considered a glutton. Whereas if someone says, did you go to the movie or did you go to the park? And you answer with yes, again, you're not considered a great logician, you're considered a jerk because it doesn't really give the answer, even though according to our logic table, that use of or is consistent with being able to say true to both of those things. This is called the inclusive or because it includes this as T up here. Typically in English, we're using what's called the exclusive or, which would put an F up here. You can build a logic system with an F here instead of a T, which just goes to show you that none of this is set in stone or revealed by nature or anything. This is our investigation of abstract reality, and we can choose to define this symbol however we like. And it just so happens that the logic that we're going to talk about in this class is based on true or true being true. Here's the implication over here. Let's try to understand what this means. Remember, when we evaluate the implication as a statement, what we're trying to understand is it true that if P is true, then Q is true? Not anything about P or Q, but if P is true, then do I get Q? That is what I'm asking. So you look here, when P and Q are both true, then yeah, then I get true implies true, so this is true. But when P is true and Q is false, that means that this statement is not true, because I have P being true and Q isn't following, so therefore P does not imply Q. These are much more challenging to think about because we have false up here. So if false, then what, right? Like if I say, if your plane lands on time, then I will pick you up from the airport, and your plane does not land on time. If I show up to the airport or if I don't, I think either way, has the promise been kept? I don't know. It's another choice here that we make. It's possible that this could go the other way, but in our logic, we are saying that both of these elements down here in the truth table are going to be T. You could build a logic that had these be F and see what happens. Again, what we're talking about in this class is logical systems. We have to understand what it is when we reason. What do we do when we reason, when we think in orderly fashion? What exactly are we doing? This propositional calculus is helping us break that down and be able to say precise things about our own thinking. Our propositions are the individual elements that we're working with. The connectives and their associated truth tables tell us what is going to be true when we combine them. And the choices we make here in our connectives give us a different logical system. Let's look at an example. One of the things we're going to need to do is come up with the truth table, fill the truth table in for certain expressions. So one way to do this is to simply take these values over here and plug them in. You'll notice that we have 3 variables now. So our truth table has 8 rows. 2 to the 3 is 8. So you're always going to have that many rows, and you could just plug them in. You could say T, T, and T. So not P is going to be not T is going to be a false here, and true or true. So we evaluate these first. False and true is false, or R, which is going to be true. False or true is true. And you could do that from this truth table up here. You could figure out all of that by breaking it down using the rules of precedence from the previous page and this truth table values here, and you can break it all down, and you can do that 8 times. There is a better way though. However, I don't recommend doing it that way. Instead, it's really helpful to us if we look at this as a normal algebraic expression. And this again is where the analogy of and being multiplication and or being addition is useful. If we look at this as a term plus another term, what we see here is that this entire expression is going to be true when the whole left-hand side term is true, or when the right-hand side term is true. So when is R going to be true? That's pretty easy, right? It's going to be true whenever R is associated with the T in the table. So we can see that we can already fill in 4 lines of this truth table just by observing the structure of the expression, because every line where R is true is going to correspond to a place where this is true. When is not P and Q going to be true? Well, it's going to be true when P is false and Q is true, which is exactly here. Well, it's these 2 places, but this one was already true. So we fill in this row right here. P is false and Q is true. Everywhere else is going to be false. You just know that because you've found every place where it's going to be true, and our propositions only have 2 values, so every place else has to be false. Let's do another one. Oh man, look at this one. Where it looks like this is just a mess. You might not even say, is this a WFF or not? But it is, that the knots are in the right place. But again, if we step back a little bit and don't get overwhelmed by the symbols, and we look at this V here and realize that that is a plus sign, that's that separates our 2 terms. So the term over here is P and not Q, and the term over here is not P and R. We can break this down and we can just look at the individual terms. So let's look at the P and not Q. When is that going to be true? Because they're separated by the or. That means this whole thing is going to be true whenever the left-hand side term is true, or whenever the right-hand side term is true. So where is P and not Q true? Well, that's going to be true when P is true and Q is false. P is true and Q is false. Not P and R. When is this going to be true? That's going to be true when P is false and R is true, which is these 2 lines here. P is false and R is true. That's it. Every place else is false. Has to be, because we've accommodated all the truths. We don't even have to go and evaluate them. We know that they are all going to be false because we only have 2 values in our logic. Not all logics have only 2 values, but ours will. We have 3 categories for our well-formed formulas. We like to come up with terms. We like to categorize things in order to speak about reality more precisely. And so that's why we have words in English. That's why we, as scientists, come up with terms for things. So We have three kinds of WFFs that we can see based on the values in their truth tables. One is called a tautology. That is one that is equivalent to T. It's always true. So if you have a truth table that has all T's, then what you have is a tautology. If you have a truth table that is all false, then what you have is a contradiction. And if you have one that has at least one T and at least one F, then we have a contingency. Contingency means that the truth value of the expression depends on the truth value of individual variables. The function itself is contingent upon the values of its inputs, whereas these are constants. This is always true, this is always false. It doesn't matter what the inputs are. These words are going to be important. You'll need to know what the words mean because they're used in the text, they'll be used in problems. They're just things that we use in this business. Let's do one more example. I want to illustrate a point here before ending. We have not P or Q and not P. So again, when is this going to be true? Let's look at not P. It's going to be true when not P is true, so when P is false. And it's also going to be true when Q and not P is true. So when Q is false, is true, and P is false. Well, that happens right here. We've already accomplished that, right? So Q and not P, that's a more restrictive requirement than simply not P alone. So this extra term doesn't add anything to this first term. If I have not P or Q and not P, since this is more restrictive, you don't even need it, right? It's gonna be false here. But really, look at this truth table. This is the exact truth table for not P, right? P is true, this expression is false. P is true, this expression is false. P is false, this expression is true. Here's not P, it's the same thing. So this whole thing here is mathematically, logically equivalent to simply not P. This is what we're going to see in the next video. We're going to look for algebraic rules to work with these sorts of expressions and manipulate them into other expressions. We're going to be able to simplify these so that we can strip out the terms in these expressions that don't add anything to the truth table. That's called logical equivalence, and it's in the next video.